Here we have the principle of mathematical induction. Now I'm going to circle this in red, the principle of mathematical induction. In the Zybook, they might have stated it a slightly different way, and there's lots of different ways you could go about stating this, the principle of mathematical induction. Here I've stated it as an if-then statement, because I think that's the most clear way with where our class is at. Okay, so the principle of mathematical induction is not something that we have to prove. It's something that we assume is true. You might want to think of it as a definition. It's something that we define to be true, and it actually isn't a definition. It's what might be called an axiom or an assumption of the logical system that we're working in. But we're not really going to talk about logical systems and axioms in this class, so you might want to just think of it as a definition. It's something we define to be true. We say this is true. But to do a proof by mathematical induction, because this is an if-then statement, we must satisfy the if part. If we satisfy this if part, then we get the then part for free. We get this part for free, the part in green. So a proof by mathematical induction is literally just this part in blue here. It's these two steps. You have the base case, that's this first step, and then the inductive step. That's the second step there. All right, but if you do the base case and the inductive step correctly, then you can conclude that the statement is true for all positive integers. Now, the purpose of this video is that I want to convince you that the principle of mathematical induction is a reasonable thing to assume to be true. All right, so I'm just going to convince you in this video, or at least I'm going to try, that the principle of mathematical induction is a reasonable assumption to make. All right, and to that end, let's assume now that we know that this if part is undeniably correct. Right, let's say that we know that this part I'm circling here is true. Okay, let's say that we've proven both of these statements, little I and little 2i. Okay. All right. So now, okay. So first of all, right, this is for all k in the positive integers, right? It's saying for all k in the positive integers, p of k implies p of k plus 1. So now let's look at k equals 1. In the k equals 1 case, so this is true, as I've underlined in green there, for all positive integers. So then if it's true for all positive integers, then it's certainly true for k, because k is one of all of the positive integers. So this is true for k equals 1. This means that p of 1 implies p of 2. This means that this statement, if p of 1, then p of 2, is true. Okay, so if p of 1, then p of 2 is true, right? So now so here we have the truth table for p of 1 equals p of 2, right here, this first truth table. Now if it's true that p of 1 implies p of 2, then we can eliminate this row because this has a false right there, right? And we're assuming that this is true. Okay, and now we also know that p of 1 is true. That's this part right here that I've circled in yellow. P of 1 is true. Okay, so we know p of 1 is true. So we know this is true, and we know this is true. So p of 1 is true. let's see, I did that in yellow, so let's do this. So here in this one, P of 1 is false, and in this one, P of 1 is false, so we can eliminate that too. So that's never going to happen. Right, and so what are we left with? We're left to conclude that P of 2 is true. Okay, so now we know that, so from this first truth table, using the fact that P of 1 implies P of 2, and P of 1 is also true, that we can conclude that P of 2 is true. Well, okay. Now we'll look at the k equals 2 case. Right, so this second statement, right, is true for all positive integers k. So it's certainly true for 2. That means that P of 2 implies P of 3 is true. And look what we got from the first one. Look what we got from this one. From this one, we got that P of 2 was true. So let's see. This tells us that we can eliminate that one. This tells us that we can eliminate that one and that one. And so then again, we can conclude that P of 3 is true. Again, we can conclude that P of 3 is true. Okay, now look, the k equals 3 case for this thing here, right? That tells us that P of 3 implies P of 4 is true. Okay, so let's see. P of 3 implies P of 4 being true. That tells us that we can get rid of that one. And then P of 3 being true, that tells us we can get rid of that and get rid of that. So then again, we can conclude now that P of 4 must be true. And so you see how we just keep doing this over and over and over again, and then we can eventually, I mean, if we were able to do this infinitely often, or infinity amount of times, then we would get that. So I mean, to get P of 5 is true. Let's see, how would we get P of 5 is true? Well, let's see, P of 4 is true. P of 4 is true, and we also know that P of 4, if we put a 4 in here, implies P of 5. And we know P of 4 is true, so that tells us that P of 5 must be true. And so on and so forth, over and over and over again, forever and ever and ever. And that's why we assume that we can conclude that for all n in the positive integers, P of n is true. Let me just run through it one more time. All right, from this one, right, we have P of 1 is true. And from this, we get that P of 1 implies P of 2 is true. P of 1 implies P of 2 is true, eliminates that. P of 1 being true, eliminates those. So then the only thing we're left for P of 2 is true there. Okay, now we have P of 2 is true. And we also know that P of 2 implies P of 3 is true. Okay, this eliminates that. This eliminates that and that. So we're left to conclude P of 3. Okay, now we've got P of 3. Well, we've got P of 3, and we also know that P of 3 implies P of 4. Now maybe you're saying, how do I know that? Right, remember that thing right there. Right, for all k. So it's certainly true for 3. So P of 3 implies P of 3 plus 1, 3 plus 1 is 4. So we got that. Okay, P of 3 implies P of 4 is true. That eliminates that. P of 3 is true. That eliminates that, eliminates that. We're left to conclude P of 4. In each case, so in the next truth table, we'd get that P of 5 was true, and then the next truth table after that, we'd get that P of 6 is true, and the next truth table after that, we'd get that P of 7 was true, and on and on and on and on and on. If we were able to do this infinitely often, then we'd be able to conclude that it was true for all P of 1, P of 2, P of 3, P of 4, P of 5, P of 6, P of 7, all the way to infinity, right? And so that's why we accept this as true. It's a reasonable assumption to make.